So the next driver of environmental change that I want to look at is the likelihood of solar output, in other words radiation from the sun, changing over time. So what we're talking about then, of course, is changes over time in the solar luminosity of the sun. The solar luminosity is the sun's total energy output. What we're going to do is we're going to take the value of 1 solar luminosity for the value today, and what I want you to have a look at here is the red line, which is actually showing through time the luminosity of the sun. So what you're actually seeing here then is that the luminosity of the sun has not been constant over geological time. If we go backwards, the Earth's 4,600 million years old. So if we go back to when the Earth was formed, you can see that the solar luminosity was probably only about 70 to 80% of what it was today. Now, as it happens, the current luminosity of today's sun, which we've scored as 1, of course, varies slightly by a fraction of a percent on an 11-year cycle that's known as the solar cycle or the sunspot cycle, and that's what's shown in the fluctuations on this graph here. And you can see here what 0.1% actually equates to in terms of the total solar irradiance. So the total solar irradiance is the amount of solar radiative energy that's incident on the Earth's upper atmosphere. The insolation then is the solar radiation energy per unit area during a given time. So what you can see here, total solar irradiance is higher here, and then it drops in this interval here, increases again, but these values are fluctuating on the order of at most 0.1% of the total luminosity today. So there's a good relationship between the amount of irradiance that's received, picked up on this axis, and the number of sunspots that are observed on the surface of the sun. So you'll see that at higher quantities of irradiance, total solar irradiance, are correlated positively with the number of sunspots. So the higher quantity of irradiance, the higher number of sunspots on the surface of the sun. And at first examination, that's slightly puzzling, because what a sunspot actually is a darker spot on the surface of the sun, and it actually represents an area in which the temperature of the sun at the surface is actually cooler than the average overall. But the key to it is that the sunspots themselves might be cooler than average, but they're accompanied by these faculae, these areas that are considerably brighter, that you see here, and thus hotter than the average. So in fact, the latter compensate for the sunspots. So the sunspots are actually paradoxically cooler, but the more sunspots you have, the more the total solar irradiance, because the sunspots are accompanied by these faculae. Now, of course, the variation in solar spot activity on an 11-year cycle that you see is picked out very nicely here, but there's also, although the data aren't necessarily as robust, there's also the possibility of longer term fluctuations than the 11-year cycle in variation in solar activity. In fact, there's an interval known as the Maunder minimum, which runs from about 1650 to 1700, which is an extended interval of low sunspot activity. And one of the things that we're going to look at is the relationship between it and a climatic phenomenon that's known as the Little Ice Age. So here's a rather elegant reconstruction of the Thames in 1677, and the key thing you'll notice about it is that it's frozen, and in fact there's an example here of 1683 of the Frost Fair, when the Thames all the way from Temple to Southwark was so frozen that a great street was built with shops and all manner of things sold. So this is an interval in which we have historical records and we have artistic renderings of this climatic phenomenon. And it illustrates the importance of art, it illustrates the importance of illustration, of written record as a mechanism of documenting climate change in an interval of time when we don't have an instrumental record. So in summary, the Little Ice Age, and it really depends what definition of it you use. Some people would start it as early as the 14th century and would have it run then up to the mid-19th century. Others identify it as an interval of time from the 16th to the mid-19th centuries. The key is it's not actually synchronous with the Maunder minimum, which straight away makes us think that the fluctuation and the reduction that we're seeing in sunspot activity can't be the sole cause of this phenomenon known as the Little Ice Age. What we have is considerable regional variation in the Northern Hemisphere through the Little Ice Age. There are in fact some areas were warmed, others varied as to how cool they became. The timing of cooling seems to have varied geographically as well, with many individual episodes that are known as the Little Ice Age through the records of Northern Europe. Whether the phenomenon extended to the Southern Hemisphere and thus was truly global in extent is really open to debate at the minute. From what we can gather from various different data sources is that we have classic signals such as the freezing of rivers and the advance of alpine glaciers, and on annual we're probably talking about temperature drops of the order of 1 degree to 1.5 degrees compared to the period of time before and the period of time after this Little Ice Age. But the really key thing that we'll come back to later is that the winters were really much colder than the interval before or after. The phenomenon is documented in Europe. It's also a scenario that plays out in Eastern North America. So we have the decline in sunspot activity as one possible cause of this Little Ice Age, though I've already made the point that the pronounced low period that you see in the Maunder minimum doesn't really seem to fit very well in terms of the timing of the Little Ice Age itself. Leaving that aside, we've also got a second problem. If you remember, we're talking about the reduction in the solar output through a single solar cycle of a fluctuation of 0.3% of the total solar irradiance. So in other words, it's a very small proportion of the budgets that's received annually that it changes by. The question is really, is that sort of fluctuation on its own sufficient to induce the temperature changes that are suggested by the Little Ice Age? In other words, can you freeze the Thames in winter simply by changing the amount of solar irradiation on a scale such as this? And what it really suggests is that what we really need is some sort of amplification of the signal to initiate the effect. So in other words, you have the signal, which is a fluctuation, say a decrease in the amount of solar radiation that's received, but some other linked factor that's driven by that serves to then amplify that climatic signal. And the result then is the effect that we see in the environmental record. Now what I'm going to do is illustrate that point to you by looking at firstly a set of data for the Northern Hemisphere, and what there are a whole series of actual case studies showing how temperature fluctuated over the period 1000 to 2000 AD, and in and around here is the interval we're interested in, associated with the Maunder minimum, for example, at around 1650 to 1700 or so. So this interval in around here, give or take a little bit more and after. And the black line in here is the average for all the paleo data, so in other words for the observed data. And what these authors have done then is they've put the average for those 7 studies in this plot here, and they've run 2 models. And if we go to the next slide, we're going to look at this interval that we're interested in further detail. So what we have then is the average paleo data shown here, and then the 2 models picked out here. So the first of the models shows all the total solar irradiation variation that can be factored into the analysis. For example, all the potential forcing factors and the 11-year sunspot cycle. And you can see that there's a relatively poor match of the data in black and the model in green. Now, the model in red is the same data, but what's happened here is that the solar forcing has been amplified by a factor of 3 to 4. And what you can see is that this data is, in large part and in certain places anyway, a much better fit to the paleo data than is the model based on the green line. So in other words, what it's suggesting is that if you want to actually take the potential causal factors, you need to add in some sort of amplifier in order to even start to match on to the observational data that's recorded from the environmental record. So again, it gives some credence to the idea that you need some sort of amplifier on the signal to initiate the effect. Now, one of the things that may be significant in terms of amplifying these sorts of climate signals is to change the amount of ozone in the stratosphere. So in other words, in the upper part of the atmosphere. And you can do so in response to solar variations, and it's known that what that will do is impact on variation in the amount of irradiance. And here's data for a computer simulation in which the total solar irradiance has been calculated, but to which a input linked to the amount of stratospheric ozone has been added. And what that suggests is that a decline in the amount of total solar irradiance coupled with a change in the proportion of stratospheric ozone is sufficient to introduce 2 significant changes to the northern hemisphere climate. Firstly, globally, including the northern hemisphere, we reduce surface temperatures by a few tenths of a degree. But look at what we do in Europe and North America. We actually have effects that are 5 to 10 times larger than typical for the globe as a whole, and that's due to a shift in atmospheric winds as a result of these changes in solar irradiance. And in fact, you can also see there are some areas that actually show an increase in temperature over the course of the year, albeit relatively small. But the key thing is these 2 phenomena, a relatively low reduction in global annual surface temperatures and a more localized extreme effect in Europe and North America, is exactly, of course, what we've seen in the actual observed paleo data associated with the environmental changes at the time of the Little Ice Age. Now, variation in the amount of total solar irradiance is not the only potential cause of the Little Ice Age. We're going to look at one other one in particular detail, but just in passing, I thought we'd have looked at this potentially very gruesome cause, and this is linked to actually human activities. The suggestion is that a reduction in agricultural activities after the Black Death would have retarded global warming and may have been sufficient to then induce the Little Ice Age. The Black Death then, 1347 to 1352 across Europe. You can see the spread of it picked out in this diagram here. Remarkably, in that period of 5 years or so, we are going to wipe out 25 million people, which is a third of the entire population of Europe at this particular time. And there's this fantastic phrase here: victims ate lunch with their friends and dinner with their ancestors in paradise. It was that pronounced its effect on the population. So this is again, if you like, a echo of events today where anthropogenic change is causing climate change. In this particular model, the decimation of the European population and the reduction in agricultural production would have then been seen a response in the climate system by a cooling of the atmosphere. There are other possible solar phenomena that may be implicated rather than just variation in the total solar irradiance. For example, there may have been fluctuations and reductions specifically in ultraviolet emissions from the sun, but we're not going to look at those in any further detail. The one we are going to spend a little bit of time looking at is the possibility that changes in volcanic activity, specifically an increase in volcanic activity, more frequent and larger scale eruptions,